So finally, the second law of thermodynamics states that a reaction is spontaneous, and remember spontaneous means product favored, if the entropy for the universe is positive. You can rewrite this then as delta S of the universe equals delta S of the system plus delta S of the surroundings. And delta S of the universe must be greater than 0 for all product-favored reactions, all product-favored irreversible processes officially, but let's just think of it as delta S of the universe greater than 0. So this is pretty important. I've been talking about how thermodynamics is kind of like a yes or a no, all right, in this chapter so far. And here's kind of the punchline of that. If you have a delta S of the universe, which is a positive number, that's a thumbs up. That's a yes, that reaction will occur. It'll be product favored, all that kind of jazz. On the other hand, if you have a value less than 0, that's going to be non-spontaneous and it won't likely happen. Delta S equals 0 is very rare. We'll talk about that more in the next chapter. So when it comes down to if a reaction will occur or not, calculate delta S of the universe, and if you have a value greater than 0, that reaction is going to occur. So what you would do if you wanted to calculate delta S of the universe, you would first calculate the entropy by the matter dispersal, delta S of the system, and then you'd calculate the entropy of the energy dispersal, delta S of the surroundings. And there are ways to do both of this. We're going to do a slightly different way most of the time in this chapter, but I'll show you an example of how you could actually calculate delta S of the universe if you so desired.
When we dissolve ammonium nitrate in water, the dissolution is an endothermic process. The temperature of the solution decreases over the course of the reaction. The reaction, though not favored energetically, is favored by entropy. It is said to be entropy-driven. As the ammonium nitrate dissolves, the entropy of the system increases. At the same time, the surroundings lose energy and experience a decrease in entropy. The increase in system entropy, however, is greater than the decrease in the surroundings entropy. Thus, the total entropy, the sum of the entropy changes in the system and surroundings, increases as demanded by the second law of thermodynamics.
So delta S of the surroundings is related to the energy, the temperature, if you will, delta H even, if you will, of the system. And so if you dissolve ammonium nitrate, it's endothermic, all right? Energy is taken from the outside and put into the inside. So that is not a product-favored reaction. However, the delta S of the system, having an ordered ammonium nitrate ionic compound dissolve into ammonium ions and nitrate ions, creates a positive delta S of the universe. And because this reaction happens, like you can see the ammonium nitrate dissolve, that means delta S of the universe must be a value greater than 0. So delta S of the surroundings doesn't want to help, but delta S of the system must be just big enough to overpower the delta S of the surroundings. So this is kind of how chemists think about things. They think about what is making the reaction happen. It's kind of an interesting process. Delta S of the universe, as an example for the making of water, we calculated earlier that came out to be minus 326.9 joules per Kelvin. So we used the entropy of the liquid water and subtracted the entropy of the hydrogen gas and the oxygen gas to figure that out. Now, the delta S surroundings for the same reaction is related to minus delta H over temperature. And this is something from physical chemistry. Please don't be too worried about it. And earlier, what we did is we calculated that the delta H of that system minus 571.70 kilojoules per mole. And we took 2 entropies of liquid water and subtracted 2 entropies of hydrogen and an entropy of oxygen to get that number. So again, this is where the table of thermodynamics can be pretty handy. So in this case then, the delta S of the surroundings, again, is minus delta H over T. So that's minus the delta H, which is already negative, minus 571.70. Let's turn kilojoules into joules, because you can see the earlier delta S of the system was in joules. We'll then divide it by the Kelvin temperature, use Kelvin in this whole chapter basically. Delta S of the surroundings, positive 1,917.5 joules per Kelvin. at this point, you have a delta S of the system and you have a delta S of the surroundings. And remember, system plus surroundings is what equals the delta S of the universe. So if you take those two values that we just calculated, the system and the surroundings, and you add them together, you're going to get the delta S of the universe. And sure enough, it comes out to be a positive number. And that's actually really good because we use liquid water all the time. And liquid water comes from hydrogen gas and oxygen gas at its base level. This had better be an entropy favored reaction, or else we wouldn't have so much liquid water around all the time. But now you can confirm why liquid water wants to happen. Positive delta S's are the ones that are spontaneous. They're going to occur.
A balloon filled with hydrogen and surrounded by air represents a potential chemical reaction. To initiate the reaction, we need to ignite the balloon. The hydrogen will combine with oxygen in the air to form water in gaseous form, releasing considerable energy in the process. At the molecular scale, the molecules of gaseous hydrogen, H2, and oxygen, O2, combine to produce H2O, water, generating heat and light. In the combustion of hydrogen and oxygen, the entropy of the atoms in the sample, or system, decreases. This decrease occurs in concert with the transfer of thermal energy to the surroundings, leading to an increase in the entropy of the surroundings. The entropy increase for the surroundings is greater than the decrease for the sample, so the net change in entropy is upward.
So the system entropy, which is a negative number, that tells that entropy is not very happy with this reaction. And it's not very happy because you have 3 moles of gas going to 2 moles of liquid. 3 moles to 2 moles is like cleaning up your room. It's making things more organized. Entropy doesn't like that. Also, you have 3 moles of gas going to 2 moles of liquid, and entropy prefers gases more disordered to liquid, so for all those reasons, the entropy is negative. On the other hand, there's so much energy given off by this reaction that the delta S of the surroundings is actually positive, so all that stored energy is released. The molecules around the reaction are just going crazy afterwards. That's why this reaction overall is happening, all right? It's the surroundings which is overpowering the system and making it spontaneous, giving it a positive delta S of the universe, all that kind of stuff. Pretty cool. So here's a question you might run into. It says, which of the following reactions should have the largest positive system entropy change? Now, what you're looking for in this problem is you want to see, for example, like gases created from liquids or solids. You want to see more moles of products than moles of reactants, things like that. So on the first one there, you have 2 moles of IF, which is a gas, iodine monofluoride, and it's making 1 mole of I2 gas and 1 mole of F2 gas. 2 moles of gas making 2 moles of gas doesn't sound like an entropy favored reaction. I think it would be closer to 0 actually. So I'm not going to put any money on that one. The second one, we've got gas, bromine, gaseous bromine going to liquid bromine. Well, liquids have less entropy than gases, so B would be out as well. And the same thing for D, by the way, down there. You've got liquid water going to solid water, which is ice. Liquids going to solids are usually entropy disfavored, so I wouldn't put any faith in that one either. However, if you look at C, and this is a little bit weird, you've got C6H6, which is a compound called benzene. It's a liquid. It's reacting with oxygen to make CO2 and water. And notice that all the products are gas. So right away, that's going to be a good indication that C is probably right, because you have all gas coming from a mixture of gas and liquids, and usually making all gas is entropy favored. But there's even more than that. You have 9 moles of gas, 6 CO2s and 3 waters, 9 moles total of gas. And on the reactant side, 15 halves, if you figure it out, is 7.5. So you have 7.5 moles of oxygen reacting with 1 mole of C6H6. So that's 8.5 moles on the reactant reactant side and 9 moles on the product side. And anytime you can go from fewer moles to more moles, that's matter dispersal, and entropy is all over that. So the answer here is definitely going to be C. You have more moles of product than you had moles of reactants. Even half of a mole is enough to make a difference. But also, one of the moles of reactant was a liquid. Everything on the product side is a gas. So for all those reasons, answer C would be the most likely positive entropy system change. There are different ways to figure out if a reaction is spontaneous or not, and this is kind of an overview. And there are basically going to be some conditions where entropy of the universe is always greater than 0 and spontaneous. So if you look on type number 1 right there, type number 1 has an entropy of the system which is positive, but you also have a delta H enthalpy of the system which is less than 0. And remember from earlier that minus delta H is proportional to positive delta S of the surroundings. So a negative delta H means you're going to have a delta S of the surroundings which is positive, and if both of those are positive, delta S of the universe will always be positive, always spontaneous. On the other hand, if you skip down to number 4 down there, if you have the opposite set of conditions, you have an endothermic delta H, which means negative delta S of the universe, and you have a negative delta S of the system, that delta S of the universe will always be less than 0, and that'll be non-spontaneous all conditions. So that would be a rough reaction to ever have it happen spontaneously. You'd have to force it to happen, stuff like that. And then you have numbers 2 and 3 types, and those basically come down to temperature dependence. And we'll talk about this here in a little bit, but you have different conditions. Sometimes it's spontaneous, sometimes it's not. There's a big temperature component to it, and we'll focus on that here in a little bit. Now, delta S of the universe is a great way to figure out if a reaction is going to occur or not, if it's spontaneous or not. But chemists really like using delta H, all right? Enthalpy is so important for lots of different reactions. And so Gibbs, down there in the lower right, was one of the great first of the American chemists. He came up with this idea to rewrite the second law of thermodynamics just a little bit. Now, delta S of the universe equals delta S of surroundings plus delta S of system. But we also saw how delta S of the surroundings equals minus delta H of the system over the temperature. And delta H is what chemists use so much. So what Gibbs did is he substituted in delta S of the surroundings equals minus delta H over T, and then he messed around with the system a little bit. He basically multiplied everything through by negative T. So then he had negative T times delta S of the universe equals delta H of system minus T delta S of the system. And basically then he, in the long run, created a new type of thermodynamic quantity, which is now called Gibbs free energy, delta G, and delta G equals minus T times delta S of the universe. So, long story short, a better version for chemists is not to use second law of thermodynamics, but use delta G equals delta H minus T delta S. This is called the Gibbs equation, because Gibbs was the first person to figure it out. And why chemists like this better is you can use delta H values directly. So all those delta H product minus delta H reactants, that's going to go right there in the delta H term. But you can do the same thing with delta S. Delta S is going to be products minus reactants for entropy values, and it also shows explicitly the temperature dependence of the entropy values. So that's what's kind of cool. The only strange thing about it, if you look at this little table right here, is that we're going to look for the opposite signs as we did for delta S of the universe. Now, if the entropy of the universe is increasing, that's spontaneous. But because of that negative part right there, that negative T, that means we're going to be looking for delta G's which are less than 0. So a negative delta G is the same effect as a positive delta S of the universe, and those are always going to be spontaneous. And likewise, if you have a delta S of the universe which is less than 0, that means your delta G is going to be greater than 0, etc., etc. So Chemists use delta G a lot more than delta S of the universe, and we're going to be actively looking for negative delta Gs. Those are spontaneous. Those are the ones that are going to occur. Positive delta Gs are non-spontaneous, and those are less likely to occur. So delta G is kind of the chemist's version, if you will, of delta S of the universe, and once you get used to it, it's actually pretty chill to use. So this Gibbs free energy is basically the total energy change for the system minus the energy change in disordering the system. So the energy change of the system, that's delta H, and you're essentially subtracting the entropy in disordering the system, which is delta S. But along the way, the temperature becomes a big factor because temperature times delta S is the factor you'll use to help calculate delta G, and we'll see the effects of that here in a little bit. But if you have an exothermic reaction with a negative delta H and an increase in entropy, a positive delta S, your delta G is going to be negative all the time, and negative delta G means that reaction is going to be spontaneous and product favored. So if you calculate a negative delta G, your reaction is going to happen. It's spontaneous. On the other hand, you can have endothermic reactions with positive delta H's. You can have negative delta S's, entropy decreasing, and those delta G's will be positive all the time. And positive delta G means you're not going to have a reaction which is going to occur as readily. So positive delta G means the reaction's not spontaneous. That's going to be more reactant favored. So if you want your reaction to go, you're hoping for exothermic and an increase in entropy, because those will always be spontaneous. On the other hand, if your reaction happens to be endothermic and with an entropy decrease, your delta G will be positive, and those will be a lot more difficult to make happen. If both delta H and delta S are the same sign, then temperature is going to be a huge factor in determining the spontaneity, i.e. determining if the reaction will occur or not, all right? And high temperatures will make one set of conditions spontaneous. On the other hand, the other set of conditions, low temperatures, will make it spontaneous. This is just something to keep in the back of your mind. And this is one reason why this equation is pretty cool, because it shows how temperature times entropy is a factor, and you have to compare it to delta H. So let's calculate the Gibbs free energy, the delta G, for this reaction. Magnesium oxide minus would be the product. Magnesium solid and half an oxygen would be the reactant. And we have here the delta H and the delta S values, okay? Now, one thing to be aware of is that delta H is almost always in kilojoules, and delta S is almost always in joules. And you can't add kilojoules to joules directly. It would be like adding a meter to a kilometer. All right, they're different types of units. So you have to turn meters to kilometers or kilometers to meters to make that happen. And it's the same thing with these. You have to turn one of them into the other. Now, because all of our answers are basically kilojoules per mole, let's turn the delta S into kilojoules. And to do that, you divide by 1,000, which means you basically move the decimal over 3 places. So if you do the math, delta H, that number, minus T delta S, well, T is going to be the Kelvin temperature, 298. We'll multiply it by minus 0.10836, turn it into kilojoules. If you do all of that, you get answer B, minus 568.9 kilojoules per mole. This is a negative delta G, so that means it's spontaneous. That reaction is going to occur. Pretty cool. So magnesium will react with oxygen to make magnesium oxide. We know that because delta G is negative. It's spontaneous. It's going to happen. This is an overview of the Gibbs free energy equation and what the possible values mean. And remember that if delta G is negative, that's spontaneous. That means the reaction is going to occur. Delta G that's positive means non-spontaneous, reactant favored. That's not as likely to occur. And here's the 4 different combinations of delta H and delta S that are possible. So exothermic, i.e. negative delta H and positive delta S, means you're going to have spontaneous delta G, i.e. negative delta G values all the time. If you flip them around, that'll always give you positive delta G values, which are reactant favored. And then again, if delta H and delta S are the same type of sign, i.e. if they're both negative or if they're both positive, then the temperature is going to play a factor. And we'll talk about that here in a little bit to see what's happening. So here we have a reaction. It has a negative enthalpy and a negative entropy. So what can be said about this reaction? A product favored at all temperatures, low temperatures, it's product favored, high temperatures, not product favored, etc., etc. 42 is a bad reference to a silly movie. Sorry about that. If you look at the Gibbs free energy, a negative delta H is going to help make delta G negative, all right? Because if negative is delta H, then delta G will be more likely negative. On the other hand, negative delta S times a negative right there, negative times negative means positive. So the entropy here is not helping delta G to be negative. As a matter of fact, delta S here being negative is going to make the reaction less likely to occur. So what we have here is a temperature dependent situation. Notice that both delta H and delta S have the same sign. They're both negative. And if they're both negative, or if they're both positive, that means temperature is going to play a factor. Now in this case, entropy is negative, and so if the temperature is big enough, then negative T delta S will be to overpower delta H. So at higher temperatures, this reaction will have a positive delta G. On the other hand, if temperature is lower, then T delta S will not be able to overpower delta H, and you'll still have product favored spontaneous reaction, i.e. a negative delta G. So for this reaction, low temperatures will make T delta S smaller than delta H. And in those situations, then, you will have a spontaneous or product-favored reaction. On the other hand, as T starts getting big, then the delta ST term will overpower delta H. And delta S is not making Gibbs free energy negative. It's going to make it positive. So at quote-unquote high temperatures, this reaction will not be spontaneous. Now, low and high are very relative, all right? Low temperatures could be like 2 Kelvin, or it could be 2000 Kelvin. It's hard to say. But past that temperature, that's when things will change, and that's the important part here. So at the lower temperatures, your delta G will be negative, and at the higher temperatures, your delta G will be positive. And that's the effect of T delta S versus delta H, if you will. There are two methods for calculating delta G. The classic method, the one that's probably best and used the most, is you find delta H and delta S separately, and then you use the Gibbs equation. However, if you do have all of the delta G values, you can do something similar to what we did with enthalpy and entropy. So the delta G of a reaction is equal to the sum of the delta G of products minus delta G of reactants. This is the last column in the mhchem.org/thermo table that we haven't used yet. We've used enthalpy since Chem 222. We used entropy in tables earlier, and the third column is the Gibbs free energy values. And you can see from the sample table there in the lower right some delta G values. Like delta H, delta G values for elements in their standard states are equal to 0. But after that, delta G values can be both positive and negative. So there's diamond, it's a positive number. On the other hand, carbon monoxide has a negative delta G. So you kind of have to look the values up. I think more of them are negative than positive, but honestly, you should look at them to make sure. So either of these methods are great. The delta H minus T delta S is probably better. It usually gives more reasonable answers than delta G products minus delta G reactants, but we'll do both of them in this class, and so you should know how to do both of them as well. Here's an example where we'll use delta G products minus delta G reactants. We're figuring out delta G for the reaction diamond plus oxygen going to carbon dioxide. So for this reaction, we take the delta G of the product, CO2, and subtract the delta G of the reactants. But you'll notice that only diamond is given, there's no O2. That's because delta G for the elements in their standard states, all those values are 0. Now diamond is given because carbon's natural form is not diamond. Graphite is much more common. You can go buy a graphite pencil pretty easy and it's not too expensive. Diamonds, of course, are much more. So that's why diamond is given. C of graphite would be equal to 0, and C of O2, which is the normal form of oxygen, is equal to 0 as well. So products minus reactants would be minus 394.4 minus 2.9 and minus 0, because O2 doesn't have a value. This comes out to be answer A, minus 397.3. So you can see all the math down there, what happens. This is a negative Gibbs free energy value, so that means this is spontaneous. And what this means is that your diamonds are going to go to carbon dioxide eventually too. So earlier I stated that diamonds are going to go to graphite, and that's true. On the other hand, this also shows diamonds will one day turn into carbon dioxide. That's what the negative value means. But again, don't panic. Don't go selling all your stuff, because kinetically, this is a very, very slow reaction. It's not going to happen in anybody's children's lifetimes. So just realize science tells some information, but you have to use a practical part about it as well. Here's an example of turning graphite into carbon dioxide and finding delta G. So similar to with diamond, it's also spontaneously going to occur, i.e. the delta G of negative 394.4 is a negative number, and negative numbers are going to happen. So again, this is why graphite as well will all turn into CO2 one day. And that's why CO2 is kind of a problem child for us right now with greenhouse gases. It's so easy to form, and it's hard to get rid of once you have it. All the delta G values, the free energy of formation values for elements in their standard states, will equal 0. And again, product favored, greenhouse gases. In this section, we're going to start talking about what's called enthalpy-driven and entropy-driven reactions. And if you have an enthalpy-driven reaction, that means you have a negative delta H, exothermic, because negative delta H's contribute to a negative delta G, and negative delta G's are spontaneous. So if you have an enthalpy-driven reaction, you have a negative delta H. Entropy-driven reactions have positive delta S values, because positive delta S times negative T makes that whole term negative, and that contributes to a negative delta G. So positive delta S reactions will be called entropy-driven.
When we pour sodium carbonate into hydrochloric acid, it dissolves rapidly to produce aqueous sodium chloride and gaseous carbon dioxide. In this case, entropy increases, and the reaction is energetically favored to occur. It is both enthalpy and entropy driven.
So this reaction is both enthalpy-driven and entropy-driven. And if you look at that reaction, gases were created, and gas creation almost always implies positive delta S. So that means that reaction is definitely entropy-driven. On the other hand, wow, a lot of energy came out, bubbling and all kinds of stuff. That's negative delta H. That's exothermic. So that means that reaction is enthalpy-driven. Energy was given off. Delta H will be negative, and entropy-driven, the gases being formed there will make delta S turn positive. That reaction is going to happen almost all the time. However, not all spontaneous reactions will have both favorable delta H and delta S values, and we'll look at some of those here. Acetylene is used in torches when people weld a lot. Acetylene reacts with oxygen to make CO2 and water. And if you've ever seen an acetylene torch, you can see that, wow, they light up. You're not supposed to look at them directly, so look away. But anyway, let's think about acetylene's combustion here a little bit more. If you calculate the enthalpy of formation for this acetylene reaction, it'll be delta H of products minus delta H reactants, so 2 CO2s and a water minus C2H2 and 5/2 O2, it comes out to be very exothermic, minus 1,238 kilojoules per mole. And again, negative numbers for enthalpy imply that enthalpy wants this reaction to go. This is an enthalpy-driven reaction. But if you do the same thing for delta S products minus delta S reactants, you get a negative 97.4 joules per Kelvin. And negative delta S's are not entropy driven. You need a positive delta S to make that entropy driven. So in this case, if you look at this long enough, you have 2.5 moles of oxygen and 1 mole of C2H2. So a total of 3.5 moles of gas going to 2 moles of CO2 and 1 mole of gaseous water going to 3 moles of gas. So 3.5 moles of gas going to 3 moles So 3.5 moles of gas going to 3 moles of gas, that's not making entropy happy. Entropy wants more disorder, and we're actually organizing it, going from more moles to less moles. So that's why the delta S value here is a negative number. So this reaction is enthalpy driven, but it is not entropy driven. You need a positive delta S to make it entropy driven. On the other hand, if you combine these at room temperature, 298 Kelvin, delta H minus T delta S, make sure you turn delta S into kilojoules per mole, you end up with a delta G, which is minus 1,209 kilojoules per mole. And that means this reaction is spontaneous, product favored. Delta S doesn't want this reaction to go, but delta H is able to overpower it and make it happen. So this is an enthalpy-driven reaction, and it makes the reaction spontaneous, but this reaction is not entropy-driven, and that's an important consideration.
In the center beaker is water at room temperature. To this we add solid ammonium nitrate. The ammonium nitrate dissolves. Usually, a reaction that occurs so readily is exothermic, but we see from the thermometer that this reaction is endothermic. The temperature of the water drops significantly. This reaction is not favored energetically, yet it still occurs.
So I've been using this example a lot. This is an example of an endothermic reaction. So that means delta H is going to be a positive number, and positive delta H's do not make this an enthalpy-driven reaction. So enthalpy does not want this reaction to go. However, you are seeing the reaction occur, all right? The solid is dissolving. So that means delta G is a negative number. It means it's spontaneous. Well, if delta G is negative, but delta H is positive, then that means that delta S must be positive, all right? Because something is making delta G negative, and it sure is not delta H. So we're going to hope here in a little bit when we calculate it that we're going to find a positive delta S because something must make this reaction occur. We're going to see a positive delta H because it's endothermic, and overall delta G should be negative. So let's look at the math. Delta H products minus reactants, sure enough, comes out to be endothermic. Energy is needed to make this reaction happen. This reaction is not enthalpy driven. On the other hand, delta S products minus reactants comes out to be positive, 108.7 joules per Kelvin. This is an entropy driven reaction as predicted, all right? And entropy here is what's making this reaction happen because, as you can tell, the solid is dissolving. If something happens, delta G is going to be negative. So delta G here, when you figure out delta H minus T delta S, make sure delta S is turned into kilojoules, etc., minus 6.7 kilojoules. So looking at these values, this reaction is spontaneous. Delta G is negative. Spontaneous means it's going to occur. This reaction is entropy driven because delta S is positive, and positive delta S contributes to negative delta G. But this reaction is not enthalpy driven. Delta H is positive, and to have an enthalpy-driven reaction, you need a negative delta H. So try to figure out these terms and how they work. They do help chemists to kind of figure out what the driving forces are, what makes reactions occur, and what makes them not occur. This reaction is product-favored, even though it's an endothermic reaction. Entropy, if you will, saves the day and makes this reaction okay. Here's another reaction. This is iron 3 oxide reacting with carbon as graphite. It makes iron metal and CO2. And what we can do to figure out the values here, you can first find delta H, products minus reactants, and that comes out to be positive 467.9. You can then find delta S, products minus reactants, comes out to be positive 560.3 joules per Kelvin. And at room temperature 298, delta G, positive 300.8 kilojoules. Now, positive delta G's mean this reaction is reactant favored at room temperature, and that means this reaction will not occur, all right? It's not going to happen at room temperature. However, let's say you have a lot of iron 3 oxide and carbon sitting around, and you'd love to make it happen. You'd love to turn it into iron and carbon dioxide. Well, if you look at the delta H and delta S values, delta H is positive. So this is not an enthalpy-driven reaction. Negative delta H's are enthalpy-driven. Enthalpy really doesn't want this reaction to go. On the other hand, delta S is a positive number. This reaction is entropy-driven. Entropy wants this reaction to go. So here you've got a condition where both delta H and delta S have the same sign. If they're both positive or both negative, temperature is going to play a factor. So what I'd like to do in this next part, let's figure out the threshold temperature by which delta G will go from being positive, which it is at room temperature, to negative. And so what we're going to do, we're going to see some temperature. It's going to be a value higher than 298, and we're going to calculate it. And that's where you go from having a positive delta G to a negative delta G. And so whatever temperature we calculate, that plus a few extra degrees will turn delta G into a negative value. And it's not too hard of a calculation to do, but this can be really important. So because we know this is entropy favored, we want to figure out the temperature at which we'll change the delta G from a positive to a negative, turn it from a non-spontaneous to a spontaneous reaction. And what you can do is just let delta G equal 0. And so 0 equals delta H minus T delta S. So delta H equals T delta S, if you put it on the other side. Solve for temperature. Temperature is delta H divided by delta S. Now again, turn delta S in joules per Kelvin into kilojoules per Kelvin. But you can see what happens there. You end up with just a Kelvin temperature. And in this problem, that's 835.1 Kelvin. So temperatures larger than this will give you negative delta G's. So if you can have your temperature be ran at, like, say, 850 Kelvin, all right, just a little bit more than 835, that's going to make your delta G a negative number. And negative delta G's are the ones that are going to happen. So again, if you've got a lot of iron 3 oxide and carbon and you really want them to react, it might be worth your time to have it run at, say, 850 Kelvin or something larger than 835.1 anyway, because at that point, the reaction becomes spontaneous. It will start occurring, and that might be worth it. And if you run a business, all right, maybe it's worth it then to have some kind of relatively expensive thing to get a temperature higher than 835.1 Kelvin. That's really, really hot. However, above those temperatures, that's where this reaction will occur, and that might be worth your time and investiture of resources to get it. That would turn your iron 3 oxide and carbon into iron and CO2. So figuring out the threshold temperature can be really important. It's only for conditions where delta H and delta S have the same sign. If delta H and delta S are both positive, the temperature you calculate, temperatures larger than that will be spontaneous. Now, if delta H and delta S are both negative numbers, you can also calculate a threshold temperature, and then temperatures under that will be spontaneous. Honestly, it's more likely that you're going to have both positive, like here, but if you do see it, that's what that would mean. So again, delta H and delta S, if they have the same sign, then calculating threshold temperatures is important. If you end up with delta H negative and delta S positive, or vice versa, your temperature comes out to be a negative Kelvin. And again, that doesn't fly in science, so that'll tell you then that this doesn't make any sense. But if they're both the same sign, these threshold temperatures can be really important. Here's an example of ice going to liquid water, and we're going to figure it out at 273 Kelvin. All right. Well, delta H, if you figure out this transformation, is a positive number, but delta S is a positive number. So delta H equals T delta S, and it's negative above a certain temperature, and it's also then positive below a certain temperature. So if you want your ice to melt, the water has to be, of course, above freezing, which which would be above 0 Celsius, above 273 Kelvin. So say at 298 Kelvin, then the entropy term is able to overpower the delta H term, and you end up with a spontaneous, i.e. negative delta G. On the other hand, at temperatures less than 273, then the opposite's going to happen, and your ice will stay the same. So this is kind of a practical use of all this stuff to figure out how ice melts. And of course, if you want your ice to melt, it has to be at a warmer temperature. On the other hand, if you want your ice to stick around, you should have it at a temperature less than 273 Kelvin. Here's a question. A given reaction is not product favored at room temperature. So what that means is delta G is going to be a positive number at room temperature. And then it says at what temperature will the reaction become product favored, and there's delta H and delta S. Well, the important part here, once again, is temperature is going to equal delta H divided by delta S, but you have to make sure that you turn delta S into kilojoules per mole to make this happen. And the temperatures come out to be Kelvin. You can translate to Celsius if you want to, stuff like that. So for this problem, it would be delta H, the 50 number, divided by delta S in kilojoules, which is 0.1, all right? 50 divided by 0.1 comes out to be 500, so the temperature here would be 500 Kelvin. And then temperatures just slightly above that, you would have negative delta Gs. So if you want this reaction to go, you could have a temperature just a little bit above 500 Kelvin, and it would start to be spontaneous. Okay, so that's the end of Chapter 12. I really appreciate you being here, and I hope we've been able to help you out with this material a little bit. If you have questions on this, there's lots of resources to help you study it some more. There's a study guide, a concept guide. You can look at the problems at the end of the chapter to figure out more things. And again, the problems at the end of the chapter in the book, the answers will be given in the back like every other answer, so you can kind of check yourself, make sure you're good to go. Practicing problems is really important with this. There's a lot of math terms, a lot of numbers to think about. It's all stuff you can do, but the more practice you have, the better you'll get at it, and you'll be good to go. All right. Thank you for spending your time with me. I do appreciate it. Good luck with your studying. Have a great day.